Hello everyone, I'm Vishwepal and I'm excited to present our work titled ArtiFact, a large-scale dataset with artificial and factual images for generalizable and robust synthetic image detection. This was a joint work performed by Mohammad Asfur Rahman, myself, Najibul Shakar, Jabir ibn Abdul Hakim, and Dr. Slikan Rawal Fatta. The task of synthetic image detection involved utilizing the unique artifacts in a generated or manipulated image to differentiate it from real images, which do not have these artifacts. The recent rise of generative models has also given way to apply synthetic image detection across broad fields, including identifying the fake product images on online e-commerce sites, removing hateful content with generated images on social media, detecting forged artworks or digital reproductions, verifying the authenticity of photos and videos in social media. One of the primary challenges in this domain is the lack of a comprehensive dataset. There is an ever-increasing number of generative models based on differing architectures such as generative adversarial networks and diffusion models. The variations in these generators can result in distinct differences in image quality, style, and noise characteristics. In addition to diversity of generators, diversity of object categories is also important because detectors need to recognize the distinctive visual characteristics exhibited by various real-world objects. Lastly, in order to reduce image size, compression and downsampling methods are often applied to images, which can impact the artifacts utilized to detect synthetic images. Such real-world impairments are often needed to be considered for a comprehensive dataset. Another challenge in synthetic image detection is the lack of a generalizable and robust solution that can handle unseen cases of generators, and works even with real-world impairments such as compression and downsampling. In this paper, we proposed the ArtiFact dataset with the goal to address the existing shortcomings of synthetic image datasets by incorporating diverse generators, object categories, and real-world impairments. We also propose a multi-class scheme to address unseen cases and filter detection method to address real-world impairments. The proposed dataset has nearly 2.5 million images, around 1.5 million of which are synthetic, and the remaining 1 million images are real. Here is a distribution of real images in the dataset. We utilize images from existing image datasets, notably LSUN, COCO, and AF, HQ, and so on. Additionally, in order to have diversity in the dataset, we incorporated images from 7 diffusion models, 13 GAN-based models, and 5 other miscellaneous models. Among these models, 5 of them partially manipulate existing images, and 20 of them fully generate synthetic image. Overall, we have included a wide variety of generators in the image generation process. The dataset contains images with categories such as humans, human faces, different types of animals, paintings of different artists, locations and different places, vehicles of different kind, and lastly, complex scenes that consist of multiple objects. In order to simulate the impairments that real-world images may encounter, a series of pre-processing steps are applied to the synthetic image. These steps involve random cropping, usaging to a standardized resolution of 200 by 200 pixels, and subsequent application of JPG compression. These procedures are implemented to consider potential image artifacts that could distort the visual content, thereby posing challenges for synthetic image detection tasks.
Hello everyone, my name is MD Asfur Rahman and I will be presenting the second part of this session. Let's take a look at the overview of our solution. Our proposed method utilizes both real and fake images from scene generators for training and testing. On the other hand, it uses fake images from unseen generators only for testing. Initially, images undergo compression and downsampling before being processed by the multi-class model with filter straight reduction. Subsequently, the predicted multi-class labels are converted into binary class labels, which are then thresholded to obtain the final prediction. Now let's delve into how our multi-class strategy with an extra class for unseen generators operates. Initially, the input image passes through the stem block with filter reduction, then through the subsequent feature extraction layers. The extracted features are then employed by the multi-class classifier for prediction. These classes can be categorized into three groups: real, seen, and unseen generator. Our proposed method ensures the model's ability to detect images from unseen generators, thereby improving its generalizability. Then the predicted multi-class label is transformed into a binary class, taking the complement of the real class prediction. Our proposed method was validated using a hybrid approach combining k-fold and group k-fold cross-validation techniques. The k-fold is applied to the scene generators, allowing it for overlap of generators between training and test data. On the other hand, the group k-fold is utilized for unseen generators, ensuring no overlap of generators between the training and the test data. Let's explore the functionality of the proposed filter stride reduction, aka FSR strategy. This method reduces the stride of the initial strided convolution or downsample layer. To gain a deeper understanding, we can refer to the animation below, where the stride is 2 before applying FSR. After FSR, the stride is reduced to 1. This approach prevents the loss of essential generator artifacts due to downsampling, thereby enhancing the model's robustness. Now, let's move to our results section. The ablation study clearly demonstrates that the multi-class method outperforms traditional binary class methods. Additionally, our proposed multi-class strategy, featuring an extra class for unseen generator, surpasses the traditional multi-class approach. Ultimately, the combination of the proposed multi-class method with proposed FSR strategy achieves the best result with an accuracy of 87.62%. Also, the proposed method was evaluated on IEEE VIP Cup 2022, where it exhibited significant dominance over other top teams. It outperformed other teams by 8.34% on test data 1, 1.26% on test data 2, 15.08% on test data 3, as measured by the accuracy metric. Lastly, the proposed method was compared to other state-of-the-art methods, demonstrating a considerable performance advantage. This solidifies its capacity to detect synthetic images with both generalization and